Okay, hello everyone. Today I will introduce the paper's name is ORC, an online competitive algorithm for recommendation and the charging schedule in electric vehicle charging network. My name is Mingyi Wang and my teammate's name is Wenyuan Zhao. Okay, firstly, let me introduce the introduction part and the background about this paper. With the customized schedule for electric vehicles EV are needed to align with their performance and request. Two types of decision for the arrival of each EV. First one is special schedule. That means which station should be assigned. The second type of decision is a temporal schedule when the EV should be charged. There are also three practical issues that arise for a CNO to solve decision-making problems. First one is uncertainty. It is challenging to predict the charging demand of each EV since it varies with time, location, and the state of each individual EV. The second problem is discretion. It is to strategically devise a charging offer which contains a recommended charging station and a corresponding energy price for each EV to choose by itself. The last one is commitment to guarantee the quality of service when making special schedules. A CNO needs to make an on-arrival commitment by reserving enough charging capacity for future temporal schedules. Okay, the next part is related work. There are two main parts. The first one is temporal scheduling of EV. Previous research has primarily focused on coordinating the charging of EVs. This coordination involves temporal load shifting strategy with the goal of mitigating the negative effect of EV charging on a power system and potentially yielding economic advantages. Some more recent studies have introduced positive price mechanisms to manage EV choices. The second part is special scheduling of EV. Some researchers have developed a pricing strategy with the objective of guiding EVs to charging station in a way that optimizes distribution of charging loads across various nodes within a transmission network. Furthermore, there have been efforts to employ a game theoretic framework to establish a special temporal scheduling system for multiple groups of public EVs competing for charging stations with limited capacity. Additional research has been conducted to explore pricing mechanisms for private EVs utilizing public EV charging station. Now, let me introduce the challenges. For challenges, there's a big challenges. It is a disparity between current online algorithms, which are mainly designed for temporal scheduling and the real-world situation where EVs act as special loads and make autonomous decisions.
Now we introduce the specific definition of our system model and the problem we want to solve specifically. So imagine that we are a charging network operator who manages M charging stations, and each station has BM chargers. So when the EV is out of power, it will send a request to the operator for a charging session. And we need to assign the idle chargers to the EV. So we assume that EV requests arrive sequentially. In the other word, at the specific time t, we will receive at most only one request. So now the most concerned questions are how much we need to cost and how much we can get from the EV and how to provide the spatial and the temporal charging service. Okay, so this is actually about the cost and responsibility of both EV and operator side. So the operator needs to provide the energy and the EV pay the bill. More specifically, the operator needs to decide two things. First, we need to offer a recommendation of the source price pair, MJ, to the EV. That is, we need to tell the EV that you can use station M to charge and pay J dollars per unit. On the other hand, when the EV receives a recommendation, it can decide whether to accept this offer or not. So on our side, the user's charging preference is actually a random variable with probability P. So if EV decides to accept this offer, we can receive the EN times RMJ dollars in total. Okay, so it is also necessary to clarify some important assumptions here for simplicity. So since we need to decide the temporal schedule, so we assume that the time slot here is fixed, and each charger has a fixed charging rate at each time slot. And then the time resources we need to cost is proportional to the energy demand EN. Also, we need to assume that each EV has a fixed choice probability over the recommended station price pairs, which means that the preference is kind of an IID random variable, PMJ. So the last assumption we also need to care about is that we assume each EVN only receive one recommendation. So the cases with multiple recommendations can be easily extended from this simple problem. Okay, then the goal of this paper is to maximize the total revenue we receive from the users. So the intuition is that we want to recommend the higher price to earn more money and serve as many users as possible at one time. However, if the price is too high, it may increase the instant reward, but the users may have a lower preference, so that we may lose some users. So the problem is not trivial, and at last we want to maximize our expected reward in the long run. And the most challenging thing here is that we lack some future arrival information, which may cause two issues. The first is that the popular stations could get occupied quickly, so that some EV need to wait. And the second issue is that some chargers are occupied by some earlier arrivals with less payment, which may all harm our total reward. So therefore, we need to design an online policy to make better decisions without any knowledge about the future arrivals. So using the knowledge we learned from the class, we need to find the policy, the online policy with minimum competitive ratio. So note that the competitive ratio is defined as the largest value of the optimal policy reward divided by the online policy reward. So we can start from something earlier, easier with more, with less certainty, with more certainty here. Okay. So that is the optimal policy. So the optimal offline policy has the prior knowledge of all future arrivals and the EV's charging preference, P. So the optimal offline policy is actually the best solution of another auxiliary optimization here, under the condition that we know everything in the future. More specifically, we know the value of this capital N here. So we have this optimization objective to maximize the expected total reward. So the constraint here is that we need to fulfill all the energy demand and not exceed the charging resource limit, and also have all the assumptions we mentioned before. So it may be hard to derive a closed form of this problem, but we can utilize some powerful computer resources and the iterative method to find the numerical solution. Then the hardest part is how to design the online policy. So here we proposed our method, the ORC algorithm, which is following from the basic idea of bid price control. So the intuition is that a product is we first need to evaluate our product and set up a threshold price. And our product is sold only when the bid price is larger than the sum of threshold price of the product. Then this spatial time temporal scheduling problem can be reduced to three sub-objectives. The first, we need to find the appropriate threshold and evaluate our resources appropriately. And the second is we need to find the appropriate strategy of making recommendations. And the last, we need to decide the temporal charging schedule. So how to decide or how to find the appropriate threshold price? The intuition is that if more chargers are occupied, then the idle resources become tighter, and we should increase the threshold price because our available resources become more valuable. And so we define this value function phi as the cost of activating another charger at station M. And the phi is the function mapping the utilization level to the price level. The utilization level is the ratio of the occupied chargers divided and the total number of chargers. So here we do not give the formula of this phi W, but we will come back again and talk this later. But it is easy to have some feelings of this phi. That is, this phi is monotonically increasing, which means that the larger W will give you the higher phi, the higher value here. Okay, so then we move to the second objective. We need to decide the strategy of recommendations. So our goal is that when a new arrival comes, we want to get a higher expected reward. So one intuitive idea is to compare the bid price with the value of our available resources. This is how we decide the recommended source price pair. The best MJ pair, denoted as M star and J star, is given by the element that can maximize the expected profits, which is the difference between the bid price R and the value function zeta. If the bid price is lower than our value, then we don't recommend. So for example, if we evaluate that our resource is worth $15, then we won't recommend this $10 price level to the vehicle. We only recommend the price level which is higher than the $15. Okay, so the last remaining thing is that we need to design a temporal schedule to charge the vehicle. Okay, so the charging vehicle is also determined by minimizing the an objective, the total cost during this feasible charging time of this EVM. So all these auxiliary optimizations we mentioned are non-trivial and necessary. We cannot simply make the decision that assign the station M with the least value function phi to the new coming EV at this instant time T1. Because if we consider the case in the figure, we can observe that the value phi varies when the previous EV left at time T3. So it is necessary to find the temporal schedule of the that can achieve the total minimum cost and subject to the energy demand. This is how this strategy comes. So now we can draw the whole picture of our algorithm by putting all these three pieces together. So here I keep the whole algorithm from the paper because I don't want to neglect any initial conditions, assumptions, and constraints. So they are all very important, and evaluating any of them will give you a totally different result and optimal policy. Okay, so when a new session comes, we have the information of the EV's requirements and our value function. So then we can determine the source pair and the charging schedule using the strategy we mentioned before. Okay, and if the EV accept this recommendation, we can then update the occupied chargers so that we can update the value functions when the next EV comes. And then we just need to repeat this loop, and we can achieve the highest value reward. Okay. So then we will show some results and analysis.
Yeah. So now let me talk about mean results. There are two main parts about mean result. The first part is piecewise value function for IM. The function values within each segment falls between two price boundaries. The following theorem 4.2 it is used to determine phi m in which condition. In the first case, if there exists a non-decreasing phi m. In the second scenario, if the segment point takes discrete values. Also, we notice that the org's expected revenue, the formula is related to two formulas. And the next main result part is about the continuous values. Firstly, we need to introduce the asymptotic value function phi m. It is used to assume segment point a continuous value, assume BM approach infinity in sufficient conditions. We also provide detailed a formula about this function, and the following theorem 4.4 is used to finalize a bounded competitive ratio with the asymptotic value function. Now, let's talk about simulation results. The figures illustrate a comparison between the empirical ratio achieved by our proposed org algorithm and the three other benchmark online algorithms. In most arrival instance, org exhibited superior empirical ratio compared to all benchmark algorithm, making it algorithm with the highest average empirical ratio across all arrival instances. The figures also emphasize that the average empirical ratio for org is very close to 1, and it is higher than other benchmark algorithm. There are another case about average acceptance ratios. The figure displays the average acceptance ratio. For example, the ratio of the number of the server charging sessions and that of the total charging sessions. The proposed org achieves the medium average acceptance ratio to trade off the aggressiveness and conservativeness when allocating the resource without future information. Yeah. Finally, let me give you guys a conclusion. We introduced an online algorithm org, and we provide sufficient conditions for ensuring that org has a constant competitive ratio. They created a value function for org along with its associated competitive ratio. Finally, the others validated the effectiveness of org by comparing other benchmark algorithms. We also want to provide some additional insights about this article. The first one is org algorithm extension. Each EVN could receive more than one recommendations. There are other potential applications. For example, streaming service. We could employ competitive algorithm to recommend movies considering customer past performance. Also, we can use the competitive algorithm to propose products to users considering their browsing history. Okay, thank you guys.